Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture. In today's lecture, we will turn our attention to high temperature deformation called creep. And the word creep defines the time dependent deformation. We have given some introduction to this time dependency of elastic deformation. We have seen it in anelasticity. In general, we have looked at anelasticity in detail, and we also have given some examples and how the anelasticity is going to play a role in the deformation of materials. So you have to recall that chapter, and we are going to connect that anelasticity behavior. But only difference is here it is plastic deformation, right? Earlier we looked at primarily an elastic deformation, that is time dependent elastic deformation, and now it is plastic deformation. So there are several ways by which one can define creep, but simply you can just tell in the layman language this is a continuous plastic deformation under constant load or stress is called creep. Of course, it is a high temperature phenomenon, but in a very simplified definition can be like this. Depending on whether we conduct the test under the constant load or stress, the strain that we measure is different owing to slight differences in the definition of stress as true or engineering stress. This we know why we call it as true stress and engineering stress. We have already seen this. Though the constant load creep tests are most common in engineering practices. Okay, so we are going to talk about mostly on the constant load creep test. Of course, we can do constant stress creep test that requires some special setup in the machine. But most of the testing machines conventionally used in the lab is constant load creep test or creep testing machines which are being used. If you write an equation of state for strain or a strain rate as d epsilon by dt is equal to epsilon dot, normally it is represented as a rate, creep rate, which is a function of sigma, stress, temperature, gamma SF, stacking fault energy, and gamma S, surface energy, etc., including time, where sigma is stress, T temperature, stacking fault energy. Yes, I just said it. We can define the creep as a test conducted in a way that we can measure the strain over a period of time, that is 0 to t, the change in strain with respect to time, that is d dou epsilon by dou t at constant stress sigma t gamma sf gamma s dt. So we can write a creep strain in this integral form, meaning that in a creep we obtain a strain from incremental strain measured as a function of time. Very important. We are looking at dou epsilon by dou t. That clearly indicates it's an incremental strain. Okay, that's why we use this dou epsilon by dou t measured as a function of time when the state variables such as sigma, t, and so on are held constant. So that's why we have put all these state variables like this. So this is one nice way of representing the creep strain, how it can be defined or how it can be visualized. Creep strongly depends on the stress and temperature in addition to other structural variables such as grain size, stacking fault energy, grain boundary energy, and Young's modulus. Creep is not exclusively a high temperature phenomenon. Okay, so this particular sentence says that the creep is strongly depends upon the stress and temperature. Okay, that is the primary variable it depends on. Of course, we have other variables, and when it comes to define high temperature, it's something relative always, right? So high temperature for one X material need not be a high temperature for other material. So that is how this sentence is brought in. Like It's not necessarily a high temperature phenomenon again, because you can, depending upon the melting point of any material, the temperature can be defined as low temperature or high temperature, right? So that's why it is said like that. In some metal, it could be observed even at temperatures close to 0 Kelvin. Oh, yeah. So this is something somebody has reported that kind of behavior. So it is generally said like that. We will see how we will define this high temperature, low temperature phenomenon. I mean, the discrepancy. How do we normalize the creep? It's very, very important and interesting as well. Yeah. So we will now look at something called a creep curve, and which is schematized in this figure, and it is quite cluttered here, but then we will slowly look at it. But I brought this diagram because it is very illustrative and very useful if you get everything in one shot. So we will go through one by one. So what is being plotted? It is a true creep strain epsilon versus time t in hours. Okay. So the creep curve goes like this, and then so what is shown here is instantaneous strain. That is what written here. You can have a elastic component as well as a plastic component. So time dependent elastic strain or recoverable strain, time dependent plastic strain, or non-recoverable or unrecoverable strain. So this is as a two interesting components. And then the creep strain goes like this, and then it reaches a steady state, and then it again accelerates, and then fracture. It's called creep rupture or fracture. It goes like that. And basically this creep curve has been divided into three regions. That is the primary region, or secondary or steady state creep, and tertiary creep. Okay. So there are three possible regions of this curve have been described here. And what is the other curve? The other curve is the dotted line, which is an overlapping plot on this creep curve. So this dash line is a creep rate, that is epsilon dot d epsilon by dt, that is superimposed on this creep curve. So don't get confused. This is a creep rate versus time, and this is a strain versus time. There are two plots superimposed on this because it is, I just particularly showed this because we will be able to describe so many things in one place, and which is it's also very useful to correlate the parameters. Okay. So figure shows the shape of typical creep curve under the constant load and stress conditions. Okay. So typically, as I mentioned, it is done in the constant load. So typically the setup of the creep testing is also, we should know, it is nothing, it will be a similar to high temperature testing setup only. Okay, except the strain will be very, very low, and the load which we can vary will be slightly different. Rest all the same. The strain time curves diverge after some initial strain. Yeah, this is what we have just said. In a constant load test, the area of the cross section gradually decreases during the creep test, and hence the true stress continuously increases till fracture. Depending on the applied load, the instantaneous strain could also contain a small component of non-recoverable plastic strain. So this is what I just said in the beginning. So you have time-dependent, non-recoverable plastic strain. This is then followed by a primary stage called a transient creep. So this region is called a transient creep, in which the strain rate epsilon from an initial high rapidly decreases to a minimum value due to work hardening. So you look now, just look at the dotted line. The initially it is very high, and then just drops and reaches the plateau here, steady state. Okay. And we are talking about it is due to work hardening effect. So that means that you see the initially after the instantaneous strain, this curve it goes like this. So that means it work hardens. So you can just match these two curves and then see how the plateau regions are matched here. So that is the reason I just brought this figure to compare. The strain rate decreases, the strain hardening takes place. Okay, the strain increases because of the strain hardening effect. As a result, the primary stage merges tangentially into the secondary steady state creep. So this plateau is called steady state. Okay, so we will discuss in elaborate manner why it is called steady state. So what you have to understand is some material exhibiting this kind of behavior. That means that could be two equally, I would say, powerful forces acting or equally possible reaction taking place. Okay, the one which causing the work hardening and one which causing the work softening. So then only this kind of plateau region comes, steady state comes. Okay, we will see the details one by one. In this stage, there are different plausible mechanisms, but predominantly the rate of recovery due to dislocation climb. So we are talking about high temperature deformation. So obviously the dislocation climb, which is a diffusion controlled process. This also we have discussed already, right? The dislocation climb is a diffusion controlled process and the rate of work hardening due to dislocation multiplication. Of course, we know what is work hardening and so on. So during which the dislocation multiplication takes place and mutual interaction balance each other, giving rise to a steady state or a steady creep flow. So this is one very quick way of explaining this, how the steady state, reaches in this during creep deformation. We will look at the details slowly. This is the most important stage in industrial applications, and it is in this stage that design criteria for creep resistance are evolved. So very important point you have to remember. So in a creep test, during this period, that is during the steady state period only, the creep rate is measured. That is also called the minimum creep rate, MCR. We will see it soon. And that is a design parameter. So you have to remember MCR is a design parameter like yield strength. It is also a design parameter, right? So here MCR is the design parameter. We will continue to describe this. The tertiary stage is characterized by the accelerated creep, eventually leading to fracture. What is that we are saying now? We are saying this is a tertiary now. After steady state, we are quickly seeing that what is this. So this is a tertiary. You can see that the rate is very high, slope is very high, and it goes all the way up to the fracture. The tertiary stage occurs more readily when tested at high stresses and high temperatures. So all that you have to remember always is whenever you talk about tertiary stage, it is always high stresses and high temperature combination. The initiation of tertiary creep is due to a number of factors, generally common to any large scale deformation. Please understand this. So this is not a local deformation, it's a large scale deformation, and most important of them are nucleation and coalescence of voids, grain boundary sliding, which is causing intergranular fracture, or crack at grain boundary triple point junctions, and accommodation of folds in neighboring grains. So these are all some of the salient features which will clearly manifest themselves for the tertiary creep. And localized necking giving rise to a development of a three-dimensional state of stress. So necking we have discussed elaborately, right? Necking accompanies with or necking region experiences three-dimensional state of stress. This we have already studied. Microstructural changes such as coarsening of precipitate, dynamic recrystallization, and diffusional changes within the phases present in the matrix. So it is not just the above features, but the microstructural changes also will contribute to this, will accompany this tertiary creep, such as coarsening of precipitate because of very high temperatures we are talking about, or even a strain-induced precipitation also will take place. Dynamic recrystallization, because we know what is dynamic recrystallization, and diffusional changes because it's very high temperature within the phases, all will contribute to this tertiary creep. So now we will see something called activation energy in creep. What is this? So we have just looked at all the the consequences of this tertiary creep. Okay, so therefore creep in materials can be classified into diffusion controlled and non-diffusion controlled mechanisms. Very important point. So now we are now trying to classify the creep mechanisms, because we are saying too many things are happening in the material as the creep deformation proceeds. So the primary classification come under these two categories. One is diffusion control and non-diffusion controlled mechanisms. And it is well established that diffusion controlled processes are governed by self-diffusion. This is again a very important point. Diffusion controlled processes are governed by self-diffusion. How do you say that? On what basis we are saying that? We will just look at it, some experimental evidence. Okay. Before we get into that, let us see the self-diffusion coefficient, how it is defined. It's given by ds is equal to d naught times e to the power minus qs by kt, where qs is the activation for self-diffusion and d naught is the frequency factor and t is the absolute temperature. For many metals, it is found that a semi-log plot of ds versus reciprocal homologous temperature Tm by T yields straight lines with slopes consistent with the choice of Qs is equal to 38 times Tm in calories per mole and Tm in Kelvin is the melting temperature. Okay, so for many metals, the Qs, that is the activation energy for the self-diffusion, is given by Qs equal to 38 Tm. How do we get this? We'll see it in a minute. The dominant process in high temperature creep is dislocation climb, which is controlled by self-diffusion. Therefore, it is possible to determine an appropriate critical temperature Tc, where above which self-diffusion is adequate enough to cause dislocation climb and hence perceptible creep. The self-diffusion coefficient can be expressed as ds is equal to b squared by t, which is equal to d naught times e to the power minus qs by kt, where b is an atomic jump distance taken as the distance of the closest approach and t is the time taken between two consecutive jumps, which in this case determines the onset of creep. T is usually taken to be about 10 to the power 3 seconds. So now we are now trying to look at the expression for the diffusion coefficient for self-diffusion in pure metals. Basically, we just try to understand how this term arises. Then we can relate to other parameters. What is this critical temperature? The critical temperature is then given by T is equal to Tc is equal to Qs by K ln T d naught divided by b square, which is equal to 38 Tm, because we are substituting this Qs here, 38 Tm by R ln T d naught by b square. What is critical temperature here? Critical temperature above which self-diffusion is adequate enough. So that means below this critical temperature, we will not assume that it is a diffusion controlled creep. Okay, like we have discussed in the classification, then we will be discussing that as a non-diffusion controlled mechanism. For the vacancy mechanism, the frequency factor D naught is approximately equal to 10 to the power minus 5 meters square per second. And with the universal constant, gas constant R is equal to 1.986 calorie per mole per Kelvin, and taking V is equal to 2.5 into the power minus 10 meter, we get Tc is equal to 0.48 Tm, approximately 0.5 Tm. So the critical temperature is worked out to be 0.5 Tm. There is another temperature which is also similar range called recrystallization temperatures. That is also very important temperature. So the critical temperature, which is also sometimes, closely related to that recrystallization temperature, right? That is also will be of similar order. The critical temperature Tc defines, the boundary for high temperature creep above which dislocation phenomena such as recovery, climb, polygonization, and dynamic recrystallization are observed, and below which strain hardening may be sustained throughout much rearrangement of resultant dislocation substance. So this Tc decides whether the creep deformation can be dominated by a diffusion controlled mechanism or non-diffusion controlled mechanism. Since creep is thermally activated, the creep rate depends on the factor exponential minus q by kt. So this is very important point to remember. So now by looking at this expression, we can say if q is large, what will happen? If the q is large, the creep rate will be small, and if q is small, the creep rate will be faster. So this is very important. If you know the activation energy, so you will be able to judge the kind of a creep rate. Therefore, those processes requiring high activation energy will be rate controlling in high temperature creep and vice versa at low temperatures. So ultimately, what is the process which is going to control the rate of the deformation, right? Another critical temperature of importance in creep is the equicohesive temperature, ECT, equicohesive temperature, which is also about 0.4 Tm. So we are now bringing a lot of critical temperatures. We are defining Tc, above which the diffusion controlled mechanism will operate. We were talking about recrystallization temperature, which is also on the order of same at 0.5 or 0.4 Tm. Now we are talking about equicohesive temperature, which is also in the range of 0.4 Tm and closely related to recrystallization temperature again. So what is the importance of this ECT? This is the temperature at which the strength of the grains and the grain boundaries is considered equal. Very important point. So at this temperature, both grain boundary and grains have a similar strength. So normally, how do we understand the grain boundaries? Grain boundaries are high energy regions, right? But in this temperature, both of them will have equal strength. So what is the use? How do we recognize the influence of this? Suppose if the operating temperature is greater than ECT, then what will happen? Okay, then what happens? Then the grain boundary will become weaker. Then the fracture will happen in the intercrystalline manner. The fracture will be intercrystalline nature. In the other ways, it is a transcrystalline region. That means the T is less than ECT, then the fracture will be transcrystalline. Or if it is the first case is intercrystalline, the second case is transcrystalline. So it gives some idea in the very beginning itself, if you know what is the temperature and so on. That is why we just look at all these parameters.